Okay, so do we have an idea of where to start on the first one? So the first thing, the first thing we're going to do is insert the magnesium into the carbon-bromine bond. So going to get that. And then we have a Grignard reagent and a ketone. And there's our ketone. And so this carbon fragment here is going to get attached to the carbonyl carbon. Okay, so there's our ketone without the ketone. We have an ethyl group attached to the magnesium bromide, so that ethyl group is going to go there. And then we still have the oxygen attached. But after aqueous workup, that's not going to be a ketone, right? Because we already have 4 bonds to carbon. That's going to be an alcohol. So for the next one, what we should probably draw to start with is our carbonyl compound. In this case, I'm going to skip drawing this step. Okay, we know the carbonyl is going to become an alcohol, and we're going to form some sort of bond here, and that's going to be to our whatever our halogenated thing is. So in this case, it's a benzene ring, and so we could also draw this like that. All right, so from a ketone, we get a tertiary alcohol, 1, 2, 3 groups. And from an aldehyde, we get a secondary alcohol, 1, 2 groups. All right, so for this one, I'm showing it in sort of the opposite way, rather than having the bromide first and then adding the carbonyl. We're showing the carbonyl first and then adding, well, the Grignard reagent's already made for us. So there's our alcohol, and then attached to the central carbon is whatever was on the magnesium bromide. In this case, is a tert butyl group. Oh, I want. I'm sorry, you have to see my face again. Hello. There we go. Okay, sorry. We could also write this as that. That's a tert-butyl group. Okay, how do we feel about the Grignard reaction? It's just two reagents you got to look for. You got to have a ketone or an aldehyde of some kind. And then you've got to have, well, eventually you have to have a Grignard reagent, which is an organic molecule with the magnesium bromide on it. But if you just have an alkyl halide like this, and then you add magnesium, that affects the same thing. All right. So the next and final carbon-carbon bond forming reaction in this section is the one we're doing in lab, and that is the Wittig reaction. And this one is particularly interesting because rather than forming a carbon-carbon single bond like the Grignard reaction, this forms a carbon-carbon double bond. So, for example, let's take acetone. And if we treat it with an alkyl halide, triphenylphosphine, and a base, we actually get that. So let's look at the arrangement of carbon atoms. So in the starting material, there's our 3 carbons. And in the reagent that we're treating it with, there's our 2 carbon atoms there. So in the product, those are the 3 carbon atoms from the ketone. And there's the 2 from the alkyl halide. So something here that doesn't happen in the Grignard reaction is that the carbon-oxygen bond is completely gone. Both the double bond, or the pi bond, and the sigma bond have been broken, and we've got a carbon-carbon double bond. Okay, so how exactly does that work? Well, these 3 reagents together make what we call the Wittig reagent. And that happens when we take the alkyl halide, which, if you remember, has 2 hydrogens on that CH2 group. And when this reacts with triphenylphosphine and some sort of base, we eliminate HBr. And what we end up with is this strange looking compound. So what's happened here? Well, we formed a bond between the central carbon and the phosphorus of the triphenylphosphine. That's that bond there. And immediately after that, we're not going to do the mechanism of this part, but then this carbon, right, this is only ending up with one hydrogen, and we lose the bromine. So this gets eliminated as HBr, and the rest of the molecule is attached to triphenylphosphine. So this is the Wittig reagent, and it's called an ylide, Ylide. Essentially, an ylide just means we have a carbon heteroatom bond where we have a negative charge on the carbon and a positive charge on the heteroatom. But the important thing here is that we now have a carbon with two substituents other than the triphenylphosphine, which is going to come off in a moment. But these two substituents, the hydrogen and the methyl group, are going to be the two substituents that end up on this carbon side of the alkene. Nope. Yep. So there's the hydrogen and the methyl group. Okay, so in the actual reaction, here's what happens. So we have our ketone. We have our ketone, and let's say right next to it, we have our Wittig reagent, aka the ylide. Okay. So this is actually a 2+2 cycloaddition. And if you remember from our little chart of what things happen, that means we're going to lose one pi bond and form one sigma bond. So we're going to make a bond between oxygen and phosphorus. By doing that. And we're going to make a carbon-carbon bond because this carbon is going to attack the electrophilic carbonyl carbon. Okay, so what does that product look like? Well, we've made a four-membered ring with oxygen, phosphorus, carbon, and carbon. Our phosphorus is a triphenylphosphine. This carbon has a methyl group and a hydrogen. And this carbon has two methyl groups. Now, as you might imagine, this molecule is kind of unstable because we've got a four-membered ring, and four-membered rings generally aren't very favorable. They're high in energy because of ring strain. And there's another sort of driving force for this reaction to continue forward, and that is that phosphorus and oxygen really like each other. And if oxygen can form an additional bond to that phosphorus, it would most certainly like to. And so in the same way that we formed a four-membered ring with two arrows, we're going to break the four-membered ring with two arrows. And that's going to give us the final product. So we're going to make a double bond between the oxygen and the phosphorus, and we're going to make a double bond between carbon and carbon. So up at the top there with the oxygen and the oxygen, God, it's Monday, and the phosphorus, we get oxygen double bond PPH3. This is triphenylphosphine oxide. This is an energy sink. Helps drive the reaction forward. And more importantly, we're going to get this organic product, which hopefully, if I've drawn it correctly, is what we predicted. So we can also write this as that, which, oops, there we go, is what I said the product was going to be. So I will ask you to predict products, but I'm not going to ask you to show how the Wittig reagent is formed. And I probably won't ask you the mechanism, but I might ask you about the side product and things like that. The main thing here is I just want to show you how that double bond is formed, because I don't know, in my opinion, this looks kind of weird. What are you doing? Just taking the oxygen off and putting a carbon on, and it's both double bonds? That seems bizarre. And the reason it can happen is because we've got sort of two steps that are required to get from this point where both of the starting materials are still separate. The ketone here is still separate from this carbon-containing group here, which was originally attached to the bromine. So once you start forming bonds between them, you get halfway there. So that forms the first carbon-carbon bond, the sigma bond, and then you form the pi bond in a second step. Okay, so let's do a different example of that. Okay, so just go ahead and tell me what the products of this. Actually, I'll do another one at the same time. Uh, okay. So, like we did for acetals with the Grignard reaction for pretty much everything so far, the first thing to do is going to be to draw the carbonyl without the carbonyl. So here's where the carbonyl was, but what has taken its place? Well, we're going from a CO double bond to a CC double bond. So it's the blue carbon. We're going to make a double bond, and the double bond is going to go to whatever carbon the halogen used to be on. So we're going to make a carbon-carbon bond. And then what do we have here? Well, there's 1, 2, 3 carbons, including the red carbon. So 1, 2, 3. Okay, so for this one, again, I'll just draw the same thing. We're going to end up with a carbon-carbon double bond. And in this case, it's going to be to this carbon. And what does this carbon have attached to it? Well, benzene ring with a methyl group. So benzene ring with a methyl group. Okay, one thing you probably have noticed about these two products is that I've only drawn one isomer of them, right? Who says that this couldn't be going this way, right? Or who says we couldn't have the benzene ring down there? And it is possible to control the regioselectivity, but for our purposes, we're just going to say that you can write either one and they're both just as correct. This usually requires some sort of other catalyst to influence it to get it to be exclusively E or Z, cis or trans, whatever you want to call it. But without any of that additional stuff, you don't get very much selectivity. Okay, questions on the Wittig reaction? Cool. All right. At this point, we're going to kind of go backwards and we're going to talk about oxygen related stuff again, but this is a pretty simple reaction. It's called Baeyer-Villiger oxidation. So this is kind of starting to get into the next chapter of stuff where we're going to be talking about other carboxylic acid derivatives like esters. And in this particular case, that's what this reaction does. We go from ketone to ester. So we have our ketone, and we're going to use, for this transformation, a peroxy acid. And peroxy acids are often, something like this, where we've got, it looks like a carboxylic acid, but it's actually got an oxygen-oxygen single bond, sort of an extra oxygen in there, hence the RCO3H rather than RCO2H. And unsurprisingly, it really wants to get rid of that oxygen. And so it's going to give it to the ketone. And our ketone becomes an ester. So that's cool. There's a lot of chemistry you can do with an ester that you can't do with a ketone. We'll talk about that a bit later. But that is a carbon-carbon bond breaking reaction. Again, those are also fairly useful. Another thing we can do with this is if we have a cyclic ketone, we can oxidize it to a cyclic ester, and cyclic esters are lactones, pretty important biomolecules. So if we take cyclopentanone and treat it with a peroxy acid, we get this six-membered ring lactone. And that's just an extension of what we did up here, right? If these two R groups are attached to each other like this, then at the end, the two R groups are still going to be attached to each other around the bottom of the ring, except we've just installed an oxygen. So notice here that the ring size goes from 5 to 6 because we've just added an oxygen atom into the ring. Now, who said that R and R are the same thing? What if the two are different? How do you pick which R group to put the ester oxygen on? So for asymmetrical ketones, the oxidation is regioselective. So the likelihood to end up on the ester oxygen is as follows. So it goes tertiary, then secondary, Secondary and phenyl are roughly the same. And then primary, and then methyl. So in practice, what does that mean? Well, if we take acetophenone and do a Baeyer-Villiger oxidation, what's going to end up on the ester oxygen? Well, we don't have a tertiary. We don't have a secondary. Well, we have a phenyl group, primary and methyl. Okay, so we've got a phenyl group here and a methyl group here. And so the group that ends up on the ester oxygen is going to be the phenyl group. All right, so that means there's our phenyl group. So there's our ester oxygen next to a carbonyl with a methyl group. So I know I've kind of flipped that upside down, but could also write it like this. Or if we have a cyclic ketone like this one's asymmetrical because this side here is, well, this is primary because other than this other than the bond to the carbonyl, this carbon only has one bond. But over here, sorry, primary. This one is tertiary because other than the bond to the carbonyl, we've got 1, 2, 3 bonds. So that means we're going to end up with a 5-membered ring, gone from 4 to 5. And the more substituted carbon is going to end up on the ester oxygen. And so that means that the oxygen is going to get put in here. So our 2 methyl groups are right there. Questions on Baeyer-Villiger oxidation? Lots of predicting products, not a lot of mechanism stuff. Yeah. Okay, that actually makes a good stopping point for us today. So that's all for now. I'm going to try to get the homework posted before next class, but I don't know. We'll see. We still have a lot of time until it's due, so.